Good morning everyone. Welcome to the 15th lecture of VLSI interconnects course. Today we will be discussing how to get two-pole transfer function of an RLC interconnect from the ABCD parameters. In the previous lecture what we saw was an equivalent Elmore approximation to get the two-pole transfer function, and in the previous lecture, the lecture before that, we had seen that how we can estimate the delay from a two-pole transfer function. So recall what we did in the last lecture. We introduced the inductive term. So inductive term was added to the resistive term of a one pole Elmore RC approximation. So we had an one pole RC transfer function, which is an approximation to get the Elmore delay, and to that we added an inductive term. So we added an inductive term to get the two pole transfer function. Today what we will do is that we will use the transfer function which we had derived in lecture 12 to get the two-pole transfer function. So we had in lecture 12 we had derived the transfer function based on the ABCD parameters, which was the exact and accurate transfer function. From that we will get a two-pole approximation. This lecture will be the last lecture in this module, or the last technical lecture in the module. In the next lecture, we will be looking at the simulation of RLC interconnects, the SPICE simulation on RLC interconnects, and with that we'll end this module in lecture 16. So coming to today's lecture, so let us first elaborate on what are the issues with the Elmore equivalent model which we discussed in the last lecture. The last lecture we saw the Elmore equivalent model, where we got a very elegant and very simple expression to estimate my coefficients of the polynomial in my h of s, and from that we can extract the expected delay and rise time for my RLC interconnect. But what was the issue? So how did we get the two-pole transfer function for an Elmore model? So with an Elmore model, basically we approximate my transfer function h of s with a term like this. So this is the only part which is there in the Elmore transfer functions for an RC ladder like this. I'm just showing one section of delta x. So there is a cascade going on both sides, right? So what is the actual transfer function? Actually, to get this equal to sign, so actually if I want to have an h of s equal to this, I would also have other higher order terms. So we had derived these expressions for the case of 2-stage, 3-stage, and so on. So the transfer function is not exactly only this, but there is also a second order term which already exists in the transfer function of an RC network. Now when we introduce an inductive term, what we were doing is that we started with this term of R, and then this R was replaced by a combination of RK plus LKS. So there is a subscript LKS, right? So we added this, and from here, so there was a term of S here, and then there is a already existing term of S here. So by combination of both, what we got was a some term of LC and S square, right? So there was some term of LC and S square. But what we had ignored here was that there would be existing this term here, which was a term of RC. So the contribution of RC terms to S square was ignored in this analysis. So there would be an additional term. So there should be a term of R and C and S square as well. So to get the coefficient of, so this was my B1 and my this entire thing was my B2. So Elmore equivalent model is expected to be to have some errors in the coefficient B2. So to eliminate that, what we will do today is that we will take the exact transfer function which we had derived in previous lecture, and we will use it to get a two-pole approximation. So there is fair bit of derivation which is required from you in this lecture. So please get your notes and pen ready. The lecture today is broadly based on two papers. So the first paper is from 2002. It's on the analysis of on-chip inductance effects for distributed RLC networks. And then there is another paper which is accurate analysis of interconnect trees with distributed RLC model and moment matching. So moment matching is basically matching the coefficients. Towards the end of this lecture, I will also scroll through both these papers to give you an idea of what we have discussed. So basically in this paper, if I look at this 2004 paper, it tells that section 3 gives an ABCD matrix of distributed RLC transmission line. Based on the ABCD matrix, section 3b addresses an iterative method to calculate the exact transfer function of interconnect trees. So this extends the ABCD parameter discussion which we will discuss today to an interconnect tree as well. Right, so let's get started. Simple again. So we have an interconnect like this. The resistance, inductance and capacitance per unit length is given to you. The length of my interconnect is L, and for this we had already seen that there is a characteristic impedance which is given by this expression, and there is a propagation constant which is given by this expression. Here S is equal to j omega. So if you are not familiar with this S, we had derived it in terms of j omega. I can replace j omega by S. And for this we had derived in lecture 12 that my ABCD parameters are given by cos hyperbolic. So A is given by this, my B is given by this term, and my C is given by this term, and my D is the same, is equal to A, which is given by this term. So there is a bit of confusion with the notation now, because there are ABCD parameters as well, and there is C which represents the capacitance per unit length as well. So what I will do is that I will represent my term C in the ABCD parameters with a symbol like this, just to eliminate the confusion. So in lecture 12, so let me write specifically reference to lecture 12, we had derived this expression for my transfer function, where A, B, C, D are all these cos and sine hyperbolic terms. So let us first take the simple case of an ideal source where RD is 0. So your driver resistance is RD is 0, and your load is also open. So there is no capacitance in the load. So this is basically open, and then this is just a short. There is no driver resistance or negligibly small driver resistance. In that case, if I substitute ZL tending to infinity in here and RD is equal to 0, what I would get is that my transfer function H of S is simply 1 upon A. And what is A? A is the A is cos hyperbolic gamma L. So now all we have to do is very simple. We expand cos hyperbolic gamma L using Taylor expansion, and then so we expand A in powers of S, and so that will give us H of S is equal to 1 divided by 1 plus, we will get 1 plus some coefficient into s plus some other coefficient into s square. So I would ask you to pause this video now and do this derivation on your own. It's simple. Look at the expansion for cos hyperbolic gamma L. What you also know is that the expression for gamma is in terms of R, L and C. So if you expand this A in terms of a series, you will get something like this: 1 plus cos 1 plus gamma square L square by factorial 2 plus 1 plus gamma L to the power 4 by factorial 4 and so on. Here we have gamma is equal to root over R plus LS into CS, or gamma square is this. So it makes our life simple because we already have terms of square, square and to the power 4 and so on. So now if you substitute it, you get very simply that 1 plus this term L square by factorial 2 plus this term into this term whole square into L to the power 4 by factorial 4 and so on. Since we are interested only till the powers of s square, we may ignore the other higher order terms. Now if I expand this, the first term is first thing is straightforward. This is in power of s RC L square by 2 by factorial 2. Factorial 2 is 2. So you can now see that RC L square term, this should be familiar to you. This comes out in my expression. Then there is another term of LC L square by 2 by factorial 2, and that is multiplied by s square. This is also familiar. We also got this term in my equivalent Elmore model. But now when I do the expansion of this second term in here, I would have R square C square S square. So if I do an expansion of this term here, this term would give me this, right? R square C square S square by factorial 4 into L to the power 4 plus then you have 2AB. So you have 2 RC L divided by factorial 4 S cube L to the power 4, and then you have a term of L square C square S to the power 4 by factorial 4. This is not L square, this is L to the power 4 and so on, right? So what we are interested in is that we have a term of S in here, and we have a term of S square in here. Now if I collect these terms, I can write it like this. So I have A as 1 by 1 plus RCL square by 2 plus LCL square by 2 plus R square C square by factorial 4 L to the power 4 S square. I can then ignore these higher order terms, so that's why I get an approximation. So ideally, if I don't want to write this approximation, I would have to consider all the higher order terms, but I am doing a two-pole approximation. So I just ignore the higher order terms. So this h of s can be approximately written as like in this form. And now here you can see that this is your term B1 and this term is your B2. So your B1 is RC L square by 2, which comes out to be the same as we got from the Elmore equivalent model, and your second term B2 is LC L square by 2. And then there is an additional term of R square C square L to the power 4 divided by factorial 4. Factorial 4 is I think 24, so this denominator is also much larger. Now if you compare this with the delay for equivalent Elmore model, for for you had B2 as, so from ABCD parameters you get B2 as LC L square by 2 plus R square c square L to the power 4 by factorial 4, and with Elmore equivalent model, you get your B2 as simply LC L square by 2. So this term which is missing in equivalent Elmore model is the error in the previous method, right? So this is missing in equivalent model. So you can note that, I mean, if your lengths are small, then this is r square c square divided by factorial 4, which is quite large. I mean, the denominator is quite large. So you can ignore this term compared to this term if your inductance is larger or dominating over the resistance. However, for longer length, so you can see that this term scales with the power of 4 when the length increases. So for longer length interconnects, this error might not be negligible, and you may have to consider it in your analysis. That's where this ABCD based analysis, ABCD parameter based analysis comes into picture, right? So now let us increase the complexity a bit. So now earlier in this previous analysis we took RD as 0, and the capacitance was also not there, so it was, this load was simply open. But now let us incorporate the effect of your driver resistance and the load capacitance as well. So if you have a load capacitance CL, your load impedance would be 1 by CL into S, right? So here so now you have to do the derivation. There is another, so just as I had mentioned, I am again explicitly mentioning that my capacitance capacitance per unit length is mentioned by C, and my my C parameter in the ABCD parameter is mentioned by this symbol. I've just drawn some lines above C to differentiate it. So now what I have is this, once I substitute ZL is equal to 1 by CS, my transfer function comes out to be this. Now what you have to do is a bit of tedious but not too lengthy derivation, where you have to substitute the values, the expressions for A, B, C and D in here, and collect the terms of S and S square in the denominator. So you know that A and D is equal to cos hyperbolic gamma L. You know the expansion for that. You know B is Z naught sine hyperbolic gamma L, C is sine hyperbolic gamma L divided by Z naught, and we also know the expansion for sine hyperbolic gamma L. We also know what is gamma. Gamma is simply root over R plus LS into CS, and Z naught is the ratio of root of the ratio of R plus LS and CS. So what you have, it becomes it is not that tedious actually. So when you do this expansion of sine and cos, sine, here you will have a term of gamma L, which will be common in all these things. So you can, what you can do is that for B, you can write it as Z naught into gamma L. Gamma L comes out, so again you have 1 plus gamma L square upon factorial 3 and so on, and here also you take the gamma L out, so again you have 1 plus gamma L square by factorial 3, and then gamma L to the power 4 by factorial 5 and so on. You can take gamma L out from these terms, and you will have Z naught into gamma L and gamma L divided by Z naught. You know these expressions, do this substitution, do the simplification, and finally you will get an expression like this. This would be this is a long expression, but the expression was long. I mean, recall that expression was long even when even with a equivalent Elmore model, when we were considering the driver resistance and load capacitance. Right. So if I now compare it with the this expression with the equivalent Elmore model, this term comes out to be the same. Right. So you can see that from the exact model also the coefficient of my S comes out to be the same as that for my Elmore model. Right. So you have this term. So there is no term of inductance in my expansion here. So if my inductance was 0, I would still have got my Elmore delay or the transfer function for my Elmore equivalent model. Now if I look at this term, here I have some additional terms. So what would have already been present in my Elmore model is LC L square by 2, L capital L into L into CL. This would be the be present there already, right? And then I would also these terms would be the only terms which would be present. Now all these terms are the additional terms which would have been missing in the in my previous analysis, right? So there are many terms here. So there is a term of which is dependent on L square, and then there is a term which is dependent on L cube. There are two terms which are dependent on L cube. One term consists of RD, other term consists of CL, and then there is R square C square divided by factorial 4 L to the power 4 term as well. Right, so you go through this derivation, it's important, and I will be keeping this lecture deliberately short so that you have enough time to go through this derivation. Right, so before I summarize, let me summarize this lecture. We are towards the end. The main goal here was to derive this expression. I will now show you some two papers which talk about this thing. So yeah, so the first paper which I want to show is the analysis of on-chip inductance effects for distributed RLC interconnects. Again, this is a fairly lengthy paper of 12 pages, so we cannot go through all of it, but basically I will show you some of the points which we have already discussed. So for example, there is an ABCD parameter which we will derive. So there is a characteristic impedance. So this expression you should be familiar with by this time, and then so there is this Z0, right? And so this is their circuits. There is R into dx, L into dx, C into dx. This is their distributed model. The length they have taken is to be H. There is a source resistance, they are calling it RS, we were calling it RD, and there is a load capacitance CL in here. Right, so if we go through it, there is this transfer function, the ABCD parametrics for a uniform RLC interconnect, interconnect or transmission line. They have in the appendix they have derived it in a very in a different way, but we derived this from the transmission line model. Here you have this what we are calling as gamma L is actually captured in here, right? So so we have this expression. You should be familiar with these expressions now. We have derived both of these. Based on this, what they then do is that they capture the effect of this source and load and other things, and finally you will get a transfer function of this form. So in this analysis, so in this work they consider a fourth order expansion. So they instead of 2 pole they are considering up to 4 pole. So here are the coefficients. So B1 is this, B2 is this. So B1 and B2 we have derived, I mean just now in the previous in this part we have derived this B1 and B2. They have also derived higher order terms, so B3 and B4 also they have derived. And finally what they say is that yeah, B4 is quite long. And then if we have this transfer function, the Laplace domain step response can be expressed in this form. Again, you should be familiar with this. For two terms we did for a two-pole transfer function. For a four-pole, there will be four exponents. So they are considering four exponents in their analysis, right? And here the transfer function h of s is coming out to be this expression, right? So from this they calculate these terms, and from here they estimate the uh, time domain response. So you can see there is an overshoot they have shown, right, for different values of RSCP. And so then there is a lot more to this paper. You can go through it in more detail. We cannot cover all the things here, but basically that's what they do. Later on they also approximate it to a two pole only. So the second order system is critically damped, over damped, under damped under these conditions. So we had seen done this analysis earlier, right? So this term should be familiar to you. So the conditions at which an overshoot would be present and other things. And then yeah, so let me now show you the derivation which they have. So in their derivation for the ABCD parameters, they start with simple case. So they have an infinitesimally small segment like this, right? So your V1 and V2 is connected like this. So V1 minus V2 is V1 minus V2 is equal to R, so the impedance into I2. So from here, so this is the expression which we had, and this is also the expression which we had. They have not converted it to differential equations. For infinitesimal section, you can write the relation between voltage and currents, and then that can be represented in terms of a matrix like this. Under the limit, so then there is fair. So basically then you have the cascading of these elements. So they have shown that if you are cascading these, what you would be finally getting, and then when you apply the limit, when n tends to infinity, you get an exponent, and so finally you can show that by this method also you get the same ABCD parameters. So we derived this assuming the knowledge, or say an introduction to the transmission line theory. Without introducing you to the transmission line theory also, we can derive this, provided you define some constants z0 and gamma. The physical understanding of z0 and gamma can come only from the transmission line model. So that's why it was important to consider the transmission line model for a comprehensive understanding. Now let me show you another paper which is 2 years later, which was published 2 years later. So this is again doing the same thing, but this is extending it to the RLC trees. So they call it moment matching, but by moment matching what they mean is simply this, that you have HS given by this thing. So this is what we expand H of S, right? So that can be compared with this. This is approximately equal to 1 divided by 1 plus b1s plus b2s, and then b1 and b2 can be computed from m1 and m2, right? So basically this is the time domain expression which we had derived earlier as well. So for a two-pole case, here they are using the ABCD parameters to get this. So ABCD parameters also we have seen. We have also seen these expansions. So these expansions can be used to get the ABCD for a single interconnect. Now the novel part here is that they are proposing a new simulation method for RLC interconnect trees. So if there is a tree like this, they are giving a method of how to compute the uh, transfer function from this point to the this point. So basically, for each of these nodes, there can be two branches. One they are calling it as the left and the other as right. So they are writing the ABCD parameters for the left branch and the right branch, and since it is connected here, the voltage for the left and the right would be equal, that is equation 15, and the current would be divided into two. So the whatever is the current here would be divided between the right branch and the left branch, and then they use it. There is a fair bit of um, arithmetic and algebraic manipulation that is required to finally get an expression for HS, and from HS then from HS they approximate it to the second order approximation for distributed RLC trees. So they use this again. So the main thing I want to emphasize here is that based on the ABCD parameters, they are comparing their results with the previous methods. So there is an H-spice model which is expected to be accurate. So this is indicated by the arrow here 4, and then this new method is 1. So they have shown that this new method based on ABCD parameters and H-spice is matching well. Then there is an Elmore based model, so which is indicated by 2 and 3 here. Right, so there you can see that there is this comparison between different methods. So there again, even when the overshoots is present, there also they are showing a match between, say, the Elmore and the Elmore equivalent. So for example, when an overshoot is present, then Elmore model is which is shown by 2, that does not show any overshoot because inductance is not considered. But when an inductance is considered, there is an overshoot present, but that is not as accurately captured as is captured in this case. Right, so you can again go through this paper. Let me quickly summarize what we have seen today or in this module. So in this module, we have discussed the inductive effects. We saw the distributed RLC interconnect model. We saw the transmission line theory for that. Based on the transmission line theory, we derived the transfer function of the ABCD parameters. To get the time domain response from the ABCD from the transfer function, we had two methods. We approximated the transfer function to a two-pole. So we had a two-pole transfer function, which was an approximation. For lumped model, we did an analysis that what would be the conditions for an overshoot to be present, and what would be the implications on the ringing effect and the ripples which are there. And then we saw that there is an equivalent Elmore model which was covered in lecture 14, and in this lecture we saw how to get a two-pole approximation from the ABCD parameter. So this completes the theoretical part of this module. In the next lecture, lecture 16, we will be looking at the SPICE simulation of RLC interconnects. And from lecture 17 onwards, we will be starting with the next module, which is module 3, in which we will discuss some additional effects in interconnect. The analysis which we have seen so far is by no means comprehensive. So there are many more papers on the analysis of RLC interconnects, what are the implications, then there are slight changes and modifications in how they model it. In terms of, in some places they show that there is an improvement in the accuracy, in some papers they show that there is an improvement in the time of computation that is required. So based on the requirements, different models can be selected, but if you have understood till this part, you would be able to understand most of the papers which are talking about RLC interconnects. With that, I will stop this lecture. We will meet in the next lecture. Good day.